Hi students, in this PPT I am going to explain question number 3 which is given in the handwritten note. So question number 3 deals with the design of braced slender column. So as we discussed in the first PPT, braced column is a frame which is having lateral bracings or wall to provide lateral stability. Okay, so this column will not be subjected to sway or lateral drift. So this is in this figure, this is the bracings provided, and this typical frame is termed as braced frame. Once the braced frame is subjected to lateral load, it may undergo curvature or bending like this. So two types of curvature is possible, single curvature and double curvature. This is very important. After moving to the question, you will understand more about its importance. So once the braced column is subjected to lateral load, it may undergo either single curvature or double curvature. So this profile shows the single curvature and this shows the double curvature. So moving on to the question, our question is, a braced column 300 mm by 400 mm is to carry a factored axial load of 1200 kN and factored moment of 50 kN and 30 kN with respect to the major axis and minor axis respectively at the top end. The column is bent in double curvature in both the direction with the moment at the bottom end equal to 40% of the corresponding moment at the top. Design the longitudinal reinforcement for the column if its unsupported length is 7.2 meter with an effective length ratio of 0.85 in both the direction. Use M20 concrete and Fe415 steel and provide 60 mm effective cover. So in this question it is mentioned the column we need to design is a braced column. Okay, the first two questions were dealing with the design of an unbraced column, and this particular one is showing how to design a braced column. Okay, so this is a braced column and its dimension is given 300 mm by 400 mm. So it is a rectangular section with B equal to 300 mm and D equal to 400 mm. And this particular column is carrying a factored axial load of 1200 kilonewton. So Pu is equal to 1200 kilonewton and factored moment of 50 kilonewton meter and 30 kilonewton meter with respect to the major axis and minor axis. And also both the moment is acting at the top end. Okay, so as I discussed in the previous PPT, our major axis is usually x-x axis and minor axis is y-y axis. So in this particular question, it is given at the top end of the column. So in this figure, I am showing the this is a representation of a column. So let this 2 represents the top end and 1 represents the bottom end. Okay, so in the question it is given at the top end, that is this 2 represents the top end. So at the top end the moment about x-axis is 50 kilonewton meter, that is a major axis, x-axis is 50 kilonewton meter, and about y-axis, that is a minor axis, is 30 kilonewton meter. So both the moment given in this question is at the top end. And the column is bent in double curvature. So this is the indication of double curvature. Okay, so this particular question is, this column is subjected to double curvature. It is having importance. I will explain it later in the design. So it is having a double curvature in both the direction with the moment at the bottom end equal to 40% of the corresponding moment at the top. So we know at the top end mx is 50 and my is 30. Correspondingly at the bottom end or at one end, this end, at the bottom end, the corresponding moment will be 40% of that available at the top end. That is given in the question. And it is asked to design the longitudinal reinforcement for the column if its unsupported length is 7.2 meters. So unsupported length is usually notated as L. So L is given as 7.2 meters with an effective length ratio of 0.85 in both the direction. Usually the effective length is calculated based on the support condition. Here it is directly given. We need to take the effective length as 0.85 L. Okay, in both direction means in x direction and y direction, the effective length is taken as 0.85 L, 0.85 times 7.2. And the materials used are M20 concrete and Fe415 steel, and the effective cover provided is 60. That is, small d dash is given as 60 mm. Okay, so moving on to the design, our first step is given data. So the unsupported length L is given as 7.2 meters. PU is given as 1200 kilonewton. Top end is notated as 2 and bottom end of the column is notated as 1. Correspondingly, the moment in x direction at the top is 50. So it is notated as M2x. And the moment that in y direction or moment about y axis at the top end is 30 kilonewton, which is notated as M2y. Correspondingly, M1x is the moment at the bottom end about x axis is only 40% of this 50. Okay, so which is equal to 20. And M1y is the moment in bottom end about y axis is only 40% of this 30 kilonewton meter, which is equal to 12 kilonewton meter. So these are the given data. And our next step is computation of slenderness ratio, E minimum and Mu minimum. First, we need to check the slenderness in both x-axis and y-axis. Since it is a rectangular section, we need to check the slenderness ratio in both in x-axis and y-axis. Next, we need to calculate minimum eccentricity, and next we will calculate the minimum moment due to that eccentricity. So as we discussed in the first PPT, while designing a slender column, we need to calculate or we need to consider both initial moment or internal moment and additional moment. So in the second step, we will be calculating the initial moment. Okay. So first, Lx and Ly is given as 7.2 meters, which is the unsupported length. Next, we are calculating the L effective. That is L effective in x and y direction. In the question it is given, we are taking the effective length ratio is taken as 0.85. So Lex and Ley is taken as 0.85 times 7.2, which is equal to 6.12. And by calculating the slenderness ratio Lex by D and Ley by B, we have obtained it as 15.3 and 20.4 respectively. So both the slenderness values are obtained greater than 12. So the column is slender for bending about both the axes. Both axis means about x axis and about y axis. The column is acting as slender. Next, we are going to calculate eccentricity in both x and y direction. The equation for eccentricity is about x axis. Ex minimum is L by 500 plus D by 30, which is obtained as 27.73 mm, which is greater than 20 mm. And Ey minimum is equal to L by 500 plus B by 30. As I explained earlier, this dimension is the dimension which is perpendicular to the y-axis. And here this dimension is the dimension which is perpendicular to x-axis. So the equation for Ey minimum is L by 500 plus B by 30, which is obtained as 24.4 mm, which is also greater than 20 mm. If any of the value of the if any of this Ex minimum or Ey minimum is obtained as 20 less than 20, we need to consider at least at 20 mm. And corresponding to this Ex minimum and Ey minimum, we will be obtaining Mux minimum and Muy minimum, which is respectively 33.276 kilonewton meter and 29.28 kilonewton meter. So this is the internal moment due to the eccentricity. And since it is subjected to so next is computation of initial moment. So since it is a braced column, you need to consider a close which is given in IS 456. So as per IS 456 2000, close 39.7.1 knots of this particular close, page number 72. This is the particular close mentioned in the IS 456. And according to this close, our primary moment in x and y direction. The column is raised and bent in double curvature, hence M1x and M1y are negative. So here, by considering this close, we will arrive at the equation, the primary moment in x direction, MUX is equal to 0.6 M2x minus 0.4 M1x, where 2 represents the end having larger end moment, M2 represents larger end moment, and M1 represents smaller end moment. And thus minus is taken since it is having a double curvature. Okay, so finally the equation becomes MUX equal to 0.6 M2x minus 0.4 M1x, and which is obtained as 22. And also in this clause it is mentioned this MUX should not be more than 0.4 M2x, which is equal to 20. So that is a check, and this check is satisfactory in our case. And correspondingly MUY is equal to 0.6 M2Y minus 0.4 M1Y, which is obtained as 13.2, which is also should be greater than 0.4 M2Y, which is equal to 12. And this in both MUX and MUY is satisfying this check. Okay, and the initial moment in x direction should be taken as greater of MUX and MUX minimum. Similarly, the initial moment in y direction should be taken as greater of MUY and MUY minimum. So in the previous two steps, we have calculated MUX minimum, MUY minimum, and MUX and MUY. Okay, so by comparing these four values, okay, we are going to compare MUX minimum and MUX. Whichever is the higher value we'll consider for the further design procedure. Similarly, whichever is the higher value of MUY minimum and MUY, that higher value will be considered for the further design procedure. So by comparing these two values, this set of value MUX minimum and MUY minimum is obtained higher. So this is considered as the initial moment. Okay, so that's MUIX, initial moment in x direction is taken as 33.276 and MUIY is taken as 29.28 kilonewton meter. Okay, so this is the initial moment. So next we need to calculate the additional moment. Since it is a slender column, you need to calculate the total moment. Total moment will be equal to initial moment plus additional moment. This initial moment, in the previous step we have calculated the initial moment. Next we are going to calculate the additional moment MA. Okay, this is similar to what we done in the previous two PPTs. So that's as per IS 456 2000, clause 39.7.1 and clause 39.7.1.1, which is given in page number 72. Our equation for additional moment in x direction and y direction are these two. So, and also this additional moment need to be multiplied with the reduction factor Kx and Ky. Usually we'll be calculating this Kx and Ky using its equation, but at this instance I'm going to assume a value of 0.5 for this Kx and Ky. In the previous two problems it is clear that Kx, this reduction factor, is usually in the range of 0.4, 0.5, 0.6, etc. So in this particular instant I'm going to assume Kx and Ky as 0.5. This is for providing a trial design. Okay, in order to take a trial design, in this instance I'm taking Kx and Ky as 0.5. Okay, the further design procedure is similar to the previous one. So by considering Kx and Ky as 0.5, I've calculated the additional moment in x direction as 28.092 and the additional moment in y direction as 37.452 kilonewton meter. So once we got the additional moment and initial moment, we can calculate the total moment. So MUTX is obtained as MUIX plus MAX, which is equal to 61.368, and MUTY is equal to MUIY plus MAY equal to 66.732. So the additional moment in x direction and y direction is obtained as 61.368 and 66.732 respectively. Okay, so we have obtained the total moment in both x and y direction. Next I am going to design a trial section. Okay, so here in this particular question it is having slenderness in both x and y direction. Next I am going to calculate or design a trial section. So while designing a trial section, I am going to design this column similar to uniaxial, a column subjected to uniaxial bending, a column subjected to axial load and uniaxial bending. That uniaxial moment moment in only one particular direction is calculated as resultant bending moment. This resultant bending moment is calculated using this equation 1.15 times root of mu tx square plus mu ty square. And the resultant bending moment is obtained as 104.26 kilonewton meter. And since the total moment obtained is total moment in y direction is obtained as greater than that in x direction, we are assuming that the resultant bending moment is also about the y axis. Okay. So next I am going to design a trial section which is subjected to axial load and uniaxial bending. So our axial load is Pu equal to 1200 kilonewton and Mu is the resultant bending moment 104 kilonewton meter. Okay. So next I am going to use the SP16 design charts for the design, which is similar to short column subjected to uniaxial bending. So our parameters are d dash by d equal to, which is obtained as 0.2 for a rectangular section providing equal reinforcement in all four sides, and Fy equal to 4 and 5. Our design chart is chart number 46, and I've calculated Pu by FCK BD and Mu by FCK BD square, which are respectively 0.5 and 0.144. And from chart number 46 of SP16, I have calculated P by FCK, where P is the percentage of steel. It is obtained as 0.19, and from that the percentage of steel is obtained as 3.8%. And from this equation 100 AS by BD equal to 3.8, I have calculated area of steel AS is equal to 4560 mm square. If I am providing 25 mm dia bar corresponding to this 4560, I will be obtaining the number of bars as 9.29. By rounding off, I am providing 10 numbers of 25 mm dia bars. So since I have increased the number of bars, again I am calculating the actual percentage of steel and P by FCK. So the provided percentage of steel is 4.09 and P by FCK becomes 0.204. So this is our trial design, design of trial section. By trial or by considering uniaxial bending, the design becomes, or we are providing 10 numbers of 25 mm dia bars. So next is I am going to calculate what is the actual total moment and actual additional moment and actual total moment, MA and MUT. So actual means by considering the equation for Kx and Ky, I am going to calculate what is the additional moment and total moment. Okay. So in the previous step, I have assumed Kx and Ky as 0.5 for designing a trial section. And next I am going to compare whether this trial section is safe or not. For that, I am going to calculate the actual additional moment and total moment. So this procedure is similar to the previous question. Kx and Ky is calculated using this equation, where PUZ is obtained from the equation given in IS 456 close 39.6, which is obtained as 25.63. And while considering the bending about x-axis, d dash by d is 0.15. PBX is calculated using the equation given in SP16, table 60, page number 171. K1 and K2 is calculated from SP16. K1x is obtained as 0.196 and K2x is obtained as 0.203. And by substituting the equation for K1x and K2x in the equation for PBX, we have obtained the value of PBX as 570.03. Similarly, we have calculated the reduction factor Kx in Kax as 0.684, and similarly we have calculated the reduction factor in y-axis as Kay is equal to 0.647. And next we are calculating the additional moment using this equation. So by substituting the respective values in the equation, we have obtained the additional moment in x direction as 38.43 and in y direction as 48.46. So these are the actual additional moment. And next we have calculated, correspondingly we have calculated the total moment in x direction and y direction, which is obtained as 71.706 and 77.74. And then next step, we are going to check the safety under axial load with biaxial bending. We have designed the trial section by considering axial load and uniaxial moment, but actually the slender column is subjected to biaxial moment. So next we are going to check whether this trial section is safe or not. For that, and this close equation is given in IS 456 2000 close 39.6 page number 71. The equation is MUX by MUX1 the whole raised to alpha n plus MUY by MUY1 the whole raised to alpha n should be less than 1, where MUX is the moment about x and y axis due to design load. MUX1 and MUY1 are the maximum uniaxial moment capacity for an axial load of PU. That is, if we are considering only one moment or a moment about one direction alone, what is the maximum capacity of that particular column? That is MUX1 and MUY1. And alpha n is related to the value PU by PUZ. PUZ is obtained using this equation, and for a value PU by PUZ between 0.2 and 0.8, the alpha n value varies linearly from 1 to 2. If the value of PU by PUZ is less than 2.2, we'll consider alpha n as 1, and if the value of PU by PUZ is greater than 0.8, we'll consider alpha n as 2. If the value is obtained in between 0.2 and 0.8, we'll interpolate and find out what is the value of alpha n. Okay, we'll see how we are checking the safety. So next we need to calculate, we have already calculated MUX and MUY. Okay, so next we are going to calculate what is MUX1 and MUY1. MUX1 and MUY1 is the maximum capacity of the column to resist a moment if we are considering only uniaxial bending. So that is calculated using this procedure. So PU by FCK BD is calculated, which is equal to 0.4. P by FCK we have already calculated 0.2045. So while considering bending about x-axis alone, the d dash by d value is 0.15. Using chart 45 of SP16, we have obtained mu by FCK BD square is equal to 0.18. From that, I can calculate mu, which is obtained as 172.8, which is the maximum capacity of the column in x direction. Okay, so mu x1 is equal to 172.8 kilonewton meter. Similarly, I have calculated MUY1 also. So MUY1 is obtained as 109.44. If I am considering bending about x-axis alone, so 172.8 is the maximum capacity of the column to take up a moment. And if I am considering the bending about y-axis alone, it can take up only a moment 109.44 maximum. This is the maximum capacity. Next, to calculate alpha n, I am going to calculate PU by PUZ, which is obtained as 0.468 PU, and PUZ already we have calculated. So its fraction, or this value has obtained as 0.468, which is in between 0.2 and 0.8. By linearly interpolating, we have obtained alpha n as 1.447. So by substituting in this equation, I have obtained MUTX by MUX1 the whole raised to alpha n plus MUTY by MUY1 the whole raised to alpha n is obtained as 0.89. As per this clause, this should be obtained as less than or equal to 1. Since we have obtained it as 0.89, which is less than 1, our design section is safe. Our trial section, the designed trial section is safe for bending about or biaxial bending also. So this is a typical example for braced column, design of braced column. Hope you all understood this. Please refer the handwritten notes while listening to this lecture. So thank you. So our first question we are dealing with how to check the adequacy of a given design. Second question we are dealing with how to design an unbraced column. And the third question is dealing with how to design a braced slender column. With this, our first module is over. So, thank you.